Tim Brady, and this is a pre-recorded presentation for the 2020 meeting of the Society for Mathematical Psychology. This is work with two co-authors, Mark Schurgin and John Wixted, and most of what I'll describe is in this Nature Human Behavior paper that you can read for more details. Okay, so I'll talk about working memory. Working memory is this mental workspace that people are really interested in, partly because its capacity is strongly related to intelligence, and in visual working memory there's an extremely common theory that I'm sure many of you have heard, arguing that we can only hold in mind 3 or 4 items. And this sets up an intuitive mental model. It says memories are like discrete physical objects we can grab and hold, right? You can hold 3, like literally like as though there was a hand. And I think population codes and signal to noise, things that are likely to be core to understanding memory, are really hard to think about at the same time as this mentally intuitive, very discrete physical framework. And so what I'll argue today is that this discrete way of thinking is wrong, that the idea that we can only hold in mind 3 or 4 items is wrong, and that we should instead think about this in a more continuous signal to noise based way. To start, let's use an example of the task that we'll look at today, this continuous report task. So try to remember these 5 colors. And then after a delay, try to remember what color was in that location and pointed it on this color wheel. It was somewhere around there. If you do this kind of task with participants, what you find is that people have lots of errors near 0. That's good. Being near the right answer is good. But also a long, fat tail. And the dominant model of this is a mixture model that argues that there's 2 things going on here. Sometimes people do not know the item, and so they're just guessing uniformly across the wheel. And sometimes they do know the item and there's some variability in their precision in which they know them. Maybe there's a normal distribution or a mixture of normal distributions or whatever people claim. And this basically formalizes this discrete way of thinking, right? It says some of the items are just lost. They just couldn't fit in your hand, so they're gone. And this is extremely prevalent. There are hundreds and hundreds of papers that try to distinguish changes in memory precision from changes in the number of represented items using this kind of mixture model. So people argue in the case of attention that this means consciousness is discrete because items change only the guess rate when you lose consciousness, for example. Iconic memory, working memory, long-term memory, this is all over the place. Pervasive model. And there are, of course, other slightly more complex versions of this model. They all have the same kinds of things in common. They all agree that these fat tails are the critical thing, and that these fat tails reflect heterogeneity between items, that they reflect some items being really poorly represented. So variable precision models claim that those are not completely unrepresented, but really close, and other models claim they're all unrepresented. What I want to argue today is that thinking about this instead, based on sort of noisy channels, thinking about signal detection theory and similarity, explains all of this in a much simpler and more straightforward way. To start with, let's think about just 2-AFC signal detection for a memory situation. Imagine you encoded purple, and then you were asked to choose between purple and green. The usual conceptualization of this is that purple gets a boost in familiarity in the memory match signal, and so in this case a d'2 boost, 2 standard deviations, and so on average purple will tend to feel more familiar, but of course on some trials green might still feel more familiar because of noise. The critical insight of the model that we'll talk about is just to consider what happens when you have a 4-AFC task instead. In standard signal detection theory, you assume that the item you saw gets a boost in familiarity, and items you did not see don't. And for items that you didn't see that are far apart in stimulus space, that probably makes a lot of sense, right? So you've got this green item is far on the color wheel, it got no boost. This other dark green item also probably gets no boost, makes sense. The critical thing is to think about in a continuous space like this what you'd expect for similar items. That is, if we were only 1 degree apart on the color wheel, and we gave you 2 foils that were basically perceptually indistinguishable, you would have no hope of picking the right answer, right? You'd pick both purple colors exactly the same if they were only 1 degree apart. The same thing must be true for this dark purple. That is, it's very similar, so it probably gets a boost in familiarity, right? So dark purple is almost certainly more likely to be picked than green in this situation, and so dark purple is going to have some shared familiarity. Its familiarity is going to have spread to all of the purples, not just that exact color you saw. And it turns out this is the whole thing. This is the whole model that we're going to use to try to explain continuous report tasks like what I showed you. That continuous report task is basically a 360 alternative force choice. And so if there must be some spreading in familiarity to nearby colors, then maybe we can just measure that and use that to predict performance in this continuous report task. So what we're going to do is we're going to use similarity as our index of familiarity spreading. We're going to empirically measure similarity, either using a Likert task or a sort of triad similarity scaling task. And we're going to collect that in different people and fix it across all conditions. We're just going to say, what if there was just a single similarity function for this color wheel that predicted how familiarity spread? Would that explain all of people's data? And so what this results in is a signal detection model that looks like this. It's a little complicated looking, right? But the purple color you actually see gets a d prime boost of 2 here. The colors that are far apart on the color wheel all get no boost at all, but the colors that are similar to purple, those, other similar purples, get some boost, not quite as much as the original purple, but, related to the height of this curve here. And so on an individual trial, purple might feel the most familiar, but on another trial, green might feel the most familiar. And so this is just signal detection theory where we just scale each foil by the familiarity signal of each foil just scales by measured similarity. That's it. It's super straightforward. And we call this the Target Confusability Competition model, TCC. How confusable items are with the target affects how well they compete. So we call this TCC. The predictions this model makes are pretty straightforward to understand, I think. D prime 0, of course, all items compete equally well, so it's uniform. At d prime 1, the items that are similar to the target get a boost, but it's not so large a boost that all those items out in the tail that didn't get any boost can't win. Of course, an item can easily win the competition, even if it got no boost if d prime is only 1. By the time you get to d prime 3 or so, you get no more long tail, because now only items that have some familiarity boosts from having seen the target are likely to win. Those items that got 0 boost are extremely unlikely to win. And so this predicts that this is what memory errors are going to look like in continuous report tasks, that they're all going to look like this. That there's not guess rate and precision and variability and precision, 3 different ways these distributions can change shape, but just only this one knob on all of these distributions. And it turns out that's true. It turns out this provides a great fit to working memory data, that in every situation we've tested, now something like 30 different conditions on the same color wheel, it's always the case that blue being this TCC model and gray being the data, that just changing this one knob, this one parameter, perfectly fits the data, that there's no need for 3 different ways these memory distributions can change. Once you understand how they do change, how the shape changes, it just predicts everything. So here is a function of set size. So even up to set size 8, just thinking of this as a lower signal to noise, just d prime going down, perfectly predicts that shape. If you change delay, so you make people hold them in mind for longer, and set size, again, these all look like just variations on the same one parameter, just d prime drops with delay, signal to noise drops with delay. With encoding time, if you give people longer encoding times, d prime increases. But again, all of these are extremely well fit by this one parameter model that is, awful coincidental if there's 3 different ways these distributions can change shape. Even within a single distribution, so even within just one condition, which is maybe the least favorable model comparison for our model, it still does a really good job. So here I'm showing you that BIC is really well calibrated for this task, for this particular situation. This is data generated from TCC. It tends to be better fit by TCC. Data generated from the mixture model is a function of guess rate and standard deviation, tends to be better fit by the mixture model. The exceptions to this are that, of course, when guess rate is 1 and when d prime is 0, those are just the same thing. And when there is no guesses, there's some region that TCC predicts similarly to the mixture model, because then the mixture model is just basically a normal distribution. And if we look at BIC as a function of real data, so here are set size 1, 3, 6, and 8 conditions, we see that TCC is reliably preferred in almost every individual participant, the exception being at set size 1, where there are no guesses in the mixture model, so it's not super discriminative. And so this is the case. TCC is preferred in almost every individual condition, and of course the fact that there are many, many conditions that all are well fit by TCC. This also works really well in other stimulus spaces, so if you measure a different similarity function for orientation or for faces, then you again find that the memory distributions are extremely well predicted by the particular similarity function for that stimulus space, but not, say, if you use the wrong similarity function, then they're very badly predicted. Okay, so what's the origin of these similarity functions? At MathPsych, it won't surprise anyone that these don't look linear in distance along the color wheel or distance along face wheel. Instead, they look about exponential. Of course, there's a huge amount of work showing similarity and generalization are sort of approximately exponential with distance in psychological spaces. So here, our colors, for example, are in CIE lab. Color space, that's a psychologically scaled space, not a physical space. And so, for example, here's data from the Universal Law of Generalization paper. Generalization is approximately exponential. In fact, the similarity functions look even more precisely like what you might have expected than that. For example, in Nosofsky's wonderful 1992 paper, he says that this function has this similarity functions generally have two parts. There's like perceptual noise, and then this exponential similarity function. And that actually perfectly matches our data. If you measure perceptual noise with a matching task and then convolve it with an exponential, you get these green points here, whereas our two similarity measures basically perfectly line up with that. So that's to say it's an exponential, but it's a little bit flatter than you might expect near zero, because there's also perceptual confusions that happen there. Okay, so this is our model, the TCC model. This is similarity function plus signal detection. And of course it's nice that it fits the data well, but even better is to make really novel predictions, and so that's what we've tried to do. One of them is this. One of them is that there's a qualitative difference where our model says there's just one process generating all of the data from all of the items in the same way. And other models basically claim that this fat tail is caused by heterogeneity between items. That is, the items contributing to the center of the distribution are the really well represented items. The items contributing to the tail of the distribution are other items. They're items that are very poorly represented or not represented at all. So they claim that there's sort of a qualitative difference in the fat tail. What this implies is that two AFC task with just maximally different foils. So just if you see purple, then you're asked to do purple versus green, just at 180 degree apart on the color wheel, is by necessity in these other models insufficient to measure all aspects of memory, right? If you just think of the two-parameter mixture model, then this basically only measures guess rate, right? The only reason you'd ever pick green over purple is if you just had an unrepresented item. The precision variation is never large enough to make you ever make a confusion of purple versus green. If you have the item in mind, you'll always know purple was more likely than green. And so precision is just unmeasured in this framework by this 2AFC. By contrast, our model says that if you just measure d prime any way you want, that you've perfectly predicted how often people will pick any set of foils, right? So imagine you measure d prime and you find that it's 3 for discriminating purple versus green. Well, now if you want to know what happens when you give 8 alternatives, you say, hey, what if I asked you to pick between these 8 colors? Then we know exactly how strong each of those colors should compete. And so we know exactly how likely people should be to pick each of those if d prime was 3. Similarly, we know exactly how often people would be to pick each of the 360 options if we gave them a continuous report task. D prime is the only thing. Everything else here is just this fixed perceptual function that we measured in different people. And so it turns out that the TCC prediction here works perfectly. So what we did is we had people do a task where on some trials they would get a 2AFC probe. Which of these 2 colors did you see? Some trials they'd get 8 choices, sometimes they'd get 32 choices, sometimes they'd get 360, they'd get a color wheel. We can measure d prime in a 2AFC task. That's just literally d prime from a 2AFC task given % correct. And then in TCC, what we can do is just plug that d prime in and predict exactly how often they should choose each of these options in these other tasks. And that's what this blue line is. This blue line is not fit to these tasks. It's only fit from this data here. And you can see it does a really good job fitting that data. Even the continuous report task is perfectly predicted just by this. In fact, you can do this differently. You can measure continuous report per subject, the d prime from TCC per subject, and measure the 2AFC d prime just the usual way. And what you find is that subject by subject, those two things are basically correlated as highly as you could expect given the noise ceiling. So 2 independent data sets fit with standard d prime and with our d prime from TCC, just exactly the same thing. And so naturally this means if you do a model comparison that compares that compares TCC's prediction given 2AFC, the prediction of continuous report, to mixture models given 2AFC predicting continuous report, you find just a huge Bayes factor preference for TCC, right? That's because TCC makes an exact prediction from the d prime and 2AFC, but given 2AFC, mixture models still have to marginalize over precision. And so you'll find every single participant has a huge preference for TCC compared to the mixture models in this generalization situation. Okay, so the target confusability competition model, TCC, is this noisy decision-making model where memories differ only in strength, only in this d prime signal to noise. There's no separate concept of number of represented items and precision. The structure of the response distribution just comes from noise and a fixed stimulus similarity function that looks exactly like what we would have expected. And this accounts for memory as a function of set size, encoding time, and delay, allows generalization across tasks and stimulus spaces, accounts for ROCs, confidence reports. Many of the measures of variable precision fall out of just signal detection theory, long-term memory, and many more. And that's all in the paper. And I think the key here is to think that the way you think about memory should not be discrete. Instead, you shouldn't think, when I remember the color of this avocado, I don't think it's green. Instead, I have some sort of population of familiarity signals in all my color channels. And they all drift up and down with noise over time, but that is my memory signal. I can answer any question based on those. So thank you very much. Thank you to my family for letting me record this, and more here.